of NEET, and in this particular session I'm going to give you all the general idea with respect to the chapters and their percentages and the number of questions which could be asked in the NEET paper, and this will be followed by a discussion of a specific chapter. So let us have a look at what all chapters are of great importance as far as NEET is concerned, as far as chemistry is concerned. So as you all know that chemistry overall is divided into three sections. You have inorganic chemistry, you have organic chemistry, and you have physical chemistry. So when it comes to inorganic chemistry, these are the chapters which we are going to look into. So here you have chemical bonding. Now this is one very important chapter from your inorganic chemistry. You can see that approximate number of questions which they are asking in the NEET paper could be between 4 to 5. So the percentage wise also is little higher. So we will be focusing on this chapter today. You have p block elements, periodic table and periodicity in properties, hydrogen, s block. These are the chapters precisely from your grade 11, right? Now when it comes to grade 12, we are dealing with inorganic chemistry again too. So here you are having coordination compounds, D and F block elements, and metallurgy. Again, these two chapters carry a good amount of weightage in your paper. Yeah, so this is with respect to inorganic chemistry. Moving to organic chemistry, very important section, very important part of the entire paper. Okay, so when it comes to organic chemistry, you are having the grade 11 chapters. Here you are having hydrocarbons and general organic chemistry, right? Again, the number of questions, if you see here, there are a good amount of questions which they can ask from organic part from your grade 11. As far as grade 12 is concerned, you are having haloalkanes and haloarenes, aldehydes, ketones, and carboxylic acid. Number of questions are 3 to 4, you can say approximate number of questions, right? Alcohols, phenols, and ethers. So these two chapters again carry a good amount of weightage. You are having organic compounds containing nitrogen, biomolecules, and polymers. And also you may expect some questions from chemistry in everyday life, environmental chemistry, and practical organic chemistry, right? But as far as the paper is concerned, these are the ones which you should be focusing more on, right? And of course, along with that, the general organic chemistry and hydrocarbons. So that was about organic chemistry. And finally, you are having a section of physical chemistry as well. So from physical chemistry point of view, from your grade 11, you have atomic structure, you have equilibrium, ionic equilibrium, redox reactions, gaseous state, that is basically your states of matter, mole and equivalent concept, and thermodynamics and thermochemistry, right? These are the chapters again from your grade 11. As far as your grade 12 is concerned, you are having chemical kinetics, electrochemistry, solid state, solutions and colligative properties, and finally you are having surface chemistry. So of all these chapters, if you see the mole concept, ionic equilibrium, along with chemical equilibrium, chemical kinetics, solutions, colligative properties, these are the ones which will carry a good amount of weightage for your NEET paper. Now apart from these chapters, obviously other chapters which have been listed here, they would also have at least one question from that particular concept. So as I told you, overall we are having inorganic, organic, and physical chemistry. So we will try to cover certain questions, certain concepts from some of these chapters. So today we are going to discuss about one specific chapter, that is nothing but chemical bonding. Now as far as chemical bonding is concerned, from your NEET perspective, what are important topics you should be concerned about? So here you need to take into consideration the VAC-PR theory or Vesper theory and hybridization. Definitely there could be some questions based on this. Bond order in resonating structures, covalent characters in ionic compounds and vice versa, ionic characters in covalent compounds, and finally MOT, that is nothing but molecular orbital theory. So you can expect some of the questions from these concepts which have been listed here. So now we are going to take up certain prototype questions dealing with these concepts. So let's have a look at the very first question here. So the question here is, in which of the following pairs the two species are not isostructural? Now, when we talk about the species being isostructural or not being isostructural, you need to have a basic understanding with respect to the Lewis structures, and of course, if you could determine the geometry or the shape of the molecule. But the prime importance here is of Lewis structure. Now, in this entire chapter, you can connect the Lewis structure to the geometry or the shape of the molecule as well as to the hybridization. So, knowing how to draw the Lewis structure is very important. So, here I am going to discuss one or two examples here of how to draw Lewis structures, and then you will get a clear understanding. And from there, we will be able to solve this particular question. So, let's have a look at very first option here, that is carbonate ion, that is CO3 2 negative, and nitrate ion, NO3 minus. So, if I consider here CO3 2 negative ion, right, how do I go about drawing its Lewis structure? So, it's very simple. So, what you need to do is you need to consider the total number of valence electrons present into this particular radical here. Okay. So, carbon, we know that it has got 4 outermost electrons. Oxygen has got 6 outermost electrons, right? But there are 3 oxygen atoms, so 6 times 3. So that makes it 18, this is 4. So total number of electrons which you are having here, there are 22 electrons. Now because you are having CO3 2 negative, it has acquired 2 electrons from outside. So that's the reason I will add 2 more electrons here, so that total number of electrons here will become 24, and hence the number of electron pairs will be 12. So the point here is I have to distribute these 12 pairs of electrons in carbonate ion. So how do I go about? I just write the central element here, that is something but carbon, and 3 oxygen atoms here. Yeah. So what is the rule? As you know that you have to draw a single covalent bond between the central element and the surrounding atoms. So what do I do here is I just simply put a single covalent bond between carbon and each of the oxygen atom. Next is I have to make sure that the octet of the surrounding atoms is complete, right? So here for oxygen I need to distribute 3 more pairs, right? So I can denote these pairs like these lines. Each single line here, each bond here represents 2 electrons, okay? So now if you notice here, octet of each of the oxygen atoms is complete, right? And I have also distributed 12 pairs of electrons in total. However, here the central element, which is carbon, it doesn't have its octet complete. So what do I do is I just remove one of the pair from oxygen and put a double bond here. Now it doesn't affect the octet of oxygen, remember. However, it is completing the octet of carbon, right? So this becomes the correct Lewis structure of the carbonate ion. Now if you notice here, the central element, which is carbon, it is having the 3 electron domains, right? 3 electron clouds. Does it have any lone pair? Answer is no. So it is having 3 electron clouds. That is what you need to remember here. Yeah. Now let's have a look at NO3 minus. So if I consider here NO3 minus, again the same drill we are going to do here. Nitrogen has 5 outermost electrons, right? Oxygen without any doubt has 6 outermost electrons times 3, so that makes it 12. This is 5. So total electrons here, if you consider, are 17, right? 17 electrons. Now, if I am dealing with NO3 minus, here 6 times 3 is 18, my bad. So 6 times 3 is 18, so this makes it 23, right? 23 electrons, and now you are adding one more electron here. So that makes it 24. So again, if you notice here, the number of electron pairs are 12, isn't it? So if I distribute these 12 pairs of electrons in NO3 minus, again your Lewis structure is going to be like this. So I can very well say here that carbonate ion and nitrate ion, in both the cases, the central element, you are having carbon and nitrogen here, right? They are surrounded by 3 electron domains, 3 electron clouds that do not have any of the lone pairs, right? So that means definitely I can say that these two structures are isostructural. They are having the same structure, right? I hope this is very much clear. Now, the same kind of concept, same kind of drill, you can do it for option B, option C, option D as well. Now, if you have a close look at option C and you try to draw its Lewis structure, you will realize that these two structures are going to be different. So if I draw the structure of PF5, it's like this: P1, 2, 3, 4 and 5. It has got trigonal bipyramidal geometry, right? So this is the structure of PF5. It is having 5 electron domains. Central element, which is phosphorus, it is having 5 electron domains, right? However, if I consider BRF5, it is 1, 2, 3, 4, 5 and there is going to be a 1 lone pair with bromine here. Remember this, okay? So now here you are going to have F, 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 F and of course F, BRF5. So even though looking at the formulae, they may seem to be having similar structures, but they are not. If you notice here, in case of BRF5, bromine in all, total, it has 6 electron domains. Now, out of these 6 electron domains, there are 5 which are bond pairs and 1 which is a lone pair. So definitely, these two structures are not the same structure, so they are not isostructural. So if I just want to list down the geometry of or the shape of BRF5, we can say that it is square pyramidal. Whereas PF5, when we look at its geometrical structure, it is going to be what? Trigonal bipyramidal. Right? So here you can clearly see that carbonated nitrate ions, they are isostructural. PCl4 plus SiCl4 will also be isostructural. Okay, they are going to have 4 electron domains, will be having tetrahedral geometry. PF5, BRF5 just now we discussed. AlF6 3 negative and SF6 also will be isostructural. They'll be having octahedral structure, octahedral geometry, right? So now, without any doubt, I'm sure you'll be able to mark this answer as C, right? So remember, whenever you are dealing with any question based on the structure, geometry, hybridization, you should know how to draw the Lewis structure. And based on the Lewis structure, you will realize how many bond pairs or how many lone pairs are associated with the central element. Let us have a look at the next question here. The hybridization of atomic orbitals of central atom Xe, that is nothing but xenon. It is obviously inert gas. So the hybridization of the central element, that is xenon, in XeF4, XeO2F2 and XeO4 respectively. So basically we have to deal with the hybridization here. Now again, as I told you, if you know the Lewis structure, you know the hybridization. So let's quickly draw the Lewis structures of these compounds. Okay. So first thing, if I consider XeO4, here we have again xenon has 8 outermost electrons, oxygen has 6 outermost electrons times 4. So that is 24. This is 8. So without any doubt, you are going to have here 32 electrons, right? So when I am having 32 electrons here, so number of electron pairs here will be 16 pairs of electrons, right? Now here, if you notice, if I have to distribute these 16 pairs of electrons, here you are going to have Xe 1, 2, 3 and 4. So draw a single covalent bond between the central element and the surrounding atom. So here you are going to have 1, 2, 3, 4. Next, make sure that the octet of the surrounding atoms is complete. So here we can say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So like this, we have distributed all the 16 pairs of electrons, right? But here you can draw a double bond between xenon and oxygen. So if I just put here a double bond like this, here also I can put a double bond, right? So the oxygen doesn't have any problem having, forming a double bond, as well as xenon can form a double bond. Now, if you see here, xenon is surrounded by 4 electron domains, 4 electron domains. So if it is surrounded by, 4 electron domains, we can say that hybridization here is nothing but sp3 hybridization. Simple, straightforward, right? Now, if you consider XeO2F2 structure, then I'll quickly draw its Lewis structure again. So here you are going to have Xe double bond O, F, F, and remember xenon will be having one lone pair. Okay, so this becomes the Lewis structure of XeO2F2. Now if you notice here in this structure, xenon is surrounded by 5 electron domains. How come 5 electron domains? There are 4 bond pairs and 1 lone pair associated with it, right? So I will say here that here xenon is having 5 domains, and because it is having 5 electron domains, clearly we can say that hybridization is going to be sp3d hybridization. Okay, and finally you are having XeOF4. So when we consider XeOF4, you are going to have Xe double bond O, single bond O, single bond O, single bond F, single bond F, single bond F, right? And of course there is going to be one lone pair associated with xenon. So this becomes the Lewis structure of XeOF4. Now if you see here that it is surrounded by total of 6 electron domains, and if it is having 6 electron domains, we can clearly see that the hybridization, 6 domains, so hybridization here is without any doubt sp3d2, right? So depending on how many electron domains the central element is surrounded by, you could have the given hybridization. So I'll just list down the hybridization here, that if you are having 2 electron domains, then the hybridization is going to be sp, simple, straightforward. If there are 3 electron domains, then the hybridization is going to be sp2. If there are 4 electron domains, just now I told you it is sp3, 5 will be sp3d2, 6 is going to be sp3, this will be sp3d, and 6 will be sp3d2, and if at all you come across any molecule having 7 electron domains, then it is going to be sp3d3. Just remember this, right? So from this, without any doubt, I'm sure you will be able to understand that your answer is going to be option sp3, sp3d and sp3d2, right? So this is basically your answer, option D. I hope you got a clear understanding, right? So again, you count the number of electron domains. Based on that, you can determine the geometry as well as the hybridization. Yeah? Okay. Moving on with the next question here. The molecule having the smallest bond angle. Now, this is a typical question which gets asked in your entrance level examination. So here you are having NCl3, AsCl3, SbCl3 and PCl3. Now, obviously, all of these, they belong to the same group, like the central element, nitrogen, arsenic, antimony and phosphorus. They all belong to the same group, that is nothing but group number 15, right? And if I consider their position here, is going to be nitrogen, phosphorus, arsenic and antimony. And we know that as and when we go down the group, what happens to the atomic size? Without any doubt, the atomic size increases, and because the atomic size is increasing, the electrons, they get more dispersed, right? Atomic size is increasing. We can say that electronegativity is decreasing. So the central element doesn't hold on to the electrons strongly, and because of which the repulsion between the bond pairs of electrons will decrease. So if I consider here NCl3 structure, it's basically like this. There is going to be one lone pair associated with nitrogen. Here you are going to have Cl, Cl and of course Cl, right? It is pyramidal structure. Now, because nitrogen is having a smallest atomic size amongst these and having maximum electronegativity, we can say that the electron density around this nitrogen is relatively higher. And because the electron density is relatively higher, these bond pairs of electrons will be little away from each other in order to minimize the repulsion. So in order to minimize the repulsion, because they are going away from each other, this particular bond angle will be more. This will be higher. However, as and when you are going down the group, like from nitrogen to phosphorus to arsenic to antimony, you will realize that in antimony its electronegativity is least, and in fact it is having a higher atomic size, larger atomic size, and because of which in case of antimony you will realize that these bond pairs of electrons, they come closer to each other, and because of which bond angle is going to decrease. So here your answer is SbCl3, antimony chloride, right? Alright, moving on with the next question here. Now this question has got a specific concept which I will be discussing here. So the question is, the bond dissociation energy of B single bond F in BF3 is 646 kilojoules per mole. Now the question is the reason for higher BF bond dissociation energy as compared to CF bond dissociation energy. Now see, it is expected that as and when we are going across the period from left to right, we are having boron and then you are having carbon. So carbon is expected to have a smaller atomic size, and if its size is smaller, then it is quite obvious that this CF bond will be shorter compared to this BF bond, right? So if CF bond is shorter compared to BF bond, then in that case CF bond should be having the higher bond dissociation energy. However, it is other way around. BF is having higher bond dissociation energy. So what could be the reason for that? Okay, so let's try to understand that. Now first and foremost thing, I'm sure that you know that the structure of BF3 here is going to be what? Trigonal planar. So BF, F and of course F, BF3. Now looking at this structure, you will realize that you do not have the octet of boron complete. Yes or no? It is having incomplete octet. And if we consider the atomic number, the electronic configuration of boron having atomic number of 5, so here you are having 1s2, 2s2, 2p, 1. And if one of the electron undergoes transition from s to p, then you are having one unpaired electron in s and two unpaired electrons in p. Now if you notice here, there is one particular orbital which is p orbital, it is empty here, right? Now that particular orbital, p orbital, which is not taking part in the bond formation, is going to remain perpendicular to the plane of this BF3 molecule. So if you are having this as a trigonal planar structure, right? So these two lobes of the p orbitals, they are going to be perpendicular to the plane of this entire molecule. Now along with that, you will realize that fluorine, right, has atomic number of 9, so it's 1s2, 2s2, 2p, 5. So when it comes to 2p5, you are having 2px2, 2py2 and 2pz1. Now it is 2pz is taking part in the sigma bond formation without any doubt, but along with that, if you notice here, it is going to have completely filled 2px2 and 2py2, right? So if I consider these p orbitals of fluorine as well, so it's going to be like this, one of the completely filled p orbital like this, and another will be perpendicular to it, right? So if I talk about this completely filled p orbital of fluorine, okay, and this is vacant p orbital of boron, because of the smaller size here, we can say that boron and fluorine, they can undergo back bonding, okay, meaning these electrons can get shifted into boron, and because of which BF bond will have certain partial double bond characters. How do I show it? It's like this. So if I consider here boron, 1, 2, 3, fluorine, fluorine, and of course fluorine. Fluorine obviously has 3 pairs of electrons here. So if these electrons, they get shifted here, so now you are having a structure like this, B, F, F, double bond F, right? Now Likewise, the double bond may get shifted. I mean, each of the fluorine can donate its electrons to boron, right? So this is the concept of something which we called as back bonding. This is the concept of back bonding which is happening in case of BF3 molecule. Now, if you consider CF4, if you consider here CF4, you will realize that the octet of carbon is already complete, right? And because the octet of carbon is already complete, it cannot show the phenomena of back bonding, right? So in other words, we can say that all these CF bonds are single covalent bonds, right? However, in BF3, you may have something which we call it as partial double bond characters. And because you are having the partial double bond characters present in BF3 molecule, you will take higher amount of energy. It will require higher amount of energy so that bond could be broken, right? So the primary reason here, as I told you, is back bonding, which is involved because of the interactions of what p orbitals of boron as well as fluorine, right? So they are involved in pi bond formation. And that's the reason you will realize that your answer here should be option B, that there is a significant p-pi interaction between boron and fluorine in BF3. And there is no possibility of such interaction between carbon and fluorine in CF4, as I told you here, because octet of carbon is already complete, right? So I hope you got the clear understanding of this particular concept, right? So in BF3, it is going to show back bonding. Moving on to the next question. The hybridization of the central atom in ICl2 plus is. Now again, if you want to know the hybridization, you should be having an idea for the Lewis structure with respect to how many bond pairs or how many lone pairs are there. In other words, total number of electron domains. So let us have a quick look at the structure of ICl2 here. So it is going to be I having total of 7 outermost electrons, right? Cl again 7 outermost electrons times 2, so that makes it 14. This is obviously 7, so this is 21. And because it is ICl2 plus, you need to subtract 1 electron from the total number of electrons. So minus 1. So the total number of electrons are 20. So how many electron pairs do we have to distribute? 10 electron pairs, right? So if I do it here, so it's going to be like this: I, single bond Cl, single bond Cl, right? Now draw a single covalent bond, 1, 2, right? Then you have to make sure that the octet of the surrounding atoms is complete. So here you are having 1, 2, 3, 1, 2, 3, right? So here we have distributed already 8 pairs of electrons. But we have to distribute in total 10, right? So definitely 2 more pairs to go. They will go with the central element, that is something but iodine. So if you notice here, iodine is having 2 bond pairs and 2 lone pairs. So in other words, we can say that it is having 4 electron domains. And if it is having 4 electron domains in its Lewis structure, without any doubt, its hybridization is going to be what? sp3, right? So definitely your answer here should be B. Yeah. So likewise, you can be asked different such questions based on the concept of hybridization. How many bond pairs, how many lone pairs are there? Please have a clear understanding of how to draw these Lewis structures. Okay. Now moving on with the next part, next question here. The decreasing values of bond angles from NH3 to SbH3 down the group 15 of the periodic table is due to decreasing lone pair bond pair repulsion, decreasing electronegativity, increasing bond pair repulsion, increasing p orbital characters in sp3. Now, this is very interesting question. You need to understand here that as and when we are going down the group for these elements, like again we are dealing with group 15 elements. So if I write these, so here you are having nitrogen, phosphorus, arsenic, antimony, right? Down the group, electronegativity is decreasing, atomic size is increasing, okay? And if you consider NH3 molecule, it is having a pyramidal structure in which the bond angle is close to 106. Basically, it is 107.5, right? But as and when we are going down the group, like in SbH3, it reduces to almost around 100. Now, the primary reason for this lies in one specific rule. You have to have a clear understanding of that particular rule. That is nothing but Dragos rule. Now, what is this rule exactly? See, there are certain cases, certain molecules in which it is perfectly fine if you do not consider the concept of hybridization. Now, there are only specific cases, not all, okay? So, if we consider all these cases, you will realize that this particular example falls into one of them. So, if I consider here the cases in which you don't have to consider the hybridization, so one of them could be at least one atom or one lone pair of the electrons which are present on the central element. Now, definitely if you see here in NH3, nitrogen is associated with one lone pair of electrons. Now, so is the case with PH3, ASH3 and SbH3. So, all of these will be having one lone pair each associated with them. Any of the elements could be from group 13, group 14, 15 or 16. These are the groups. The rule is applicable to the elements belonging to these groups and also from the period number 3rd to 7th. So, does antimony belong to a period number 3 to 7? Answer is definitely yes. Correct? The central atom has an electronegativity which is less than or equal to 2.5 because as we know, as we go down the group, electronegativity is decreasing, right? Now, what if, all these characteristics, all these cases or all these conditions are met? Then in such cases, the central element like you have SbH3 or you can take any example of PH3 as well. So, SbH3, it is expected to show sp3 hybridization. However, because of these conditions, what is happening is the higher energy levels of s and p orbitals which are taking part in the bond formation, right? So, because of that, these lone pairs of electrons which are actually belonging to the s orbitals, right? We have the general electronic configuration as ns2 np3, right? So, these ns electrons then will be reluctant to take part into hybridization and rather it will remain as it is. And these bonds which are formed between antimony and hydrogen, they are actually because of these p orbitals. So, overlapping involving p orbitals of antimony and s orbitals of the hydrogen, right? So, we can clearly say here that in this particular structure, in these bonds which are present, there is a higher percentage of p orbitals, p orbital characteristics, right? And that's precisely the reason here your answer should be D. So, as and when you are going down the group, because of the, this particular rule, that is something but Dragos rule, you have to consider the concept of not having hybridization, right? So, down the group, antimony is there, it is having a lone pair of electrons, it is belonging to the period number 13 to 16, basically it is belonging to period number 15, right? And it is below period number 3, right? So, because of all these characteristics, you cannot consider hybridization in SbH3 molecule and that's the reason these bonds which are formed will involve overlapping of p orbitals of antimony with the s orbital of hydrogen, right? So, I hope you got the clear understanding with respect to this particular question. So, we have discussed quite a few questions which are based on the Lewis structures, hybridization and the geometry of the molecules, right? Now, let us have a look at another specific concept here, that is how to find the bond order in resonating structures. Now, we very well know that bond order is nothing but the total number of bonds which are present between two atoms in a molecule. Like for example, if I consider the bond order of N2 molecule, right? So, this N2 molecule is precisely N triple bond N without any doubt. So, here we can clearly say that the bond order is 3, right? But what if you come across the resonating structures? In such a case, how do you go about finding the bond order? So if I consider the carbonate ion, we know its Lewis structure, so let us quickly draw its Lewis structure, or you can draw its geometrical figure as well. So here you are having C double bond O, single bond O, single bond O, right? This is a trigonal planar geometry of the carbonate ion. So first and foremost thing, let us draw the resonating structures here for this carbonate ion. So can we see here that these electrons are shifting here, so that these electrons will shift here. Yeah. So now another structure here you are going to have is C, single bond O. There is a double bond O. There is a single bond O. Right. One more possibility of structures here is that these electrons will shift here, right? Or rather I can say that these electrons are shifting here, so that these electrons will shift here, correct? So now you are going to have C, single bond O, double bond O, and of course single bond O here as well. So these are all the possible resonating structures, right? Now, in such a case, if I have to find the bond order, now like carbonate ion, they can ask you, for any particular ion, and if you want to draw the resonance hybrid of all these three structures, we can have it here, right? So it is C, single bond O, single bond O, and of course single bond O. So these three sigma bonds are for sure there, right? What is shifting is the pi bonds or pi electrons. So we can say here that you are going to have, partial double bonds here. And each of the oxygen atom is going to have a fractional charge of negative 2/3. So this becomes the resonance hybrid. So in such a case, how do I go about finding the bond order? So there's a direct formula which you all should be knowing. Just apply that formula, you will get the answer for the bond order, right? So bond order here is equal to, the formula is the total number of bonds present in a molecule. Total number of bonds, right? Divided by the total number of resonating structures. The total number of bonds divided by the total number of resonating structures. So now if you have a close look, here there are 1, 2, 3 and 4 bonds. Now any of these structures, if you look at, you are going to have 4 as a total number of bonds, right? And clearly in front of you, you can see there are how many resonating structures? 3 resonating structures, right? So if I write here, you are going to have total number of bonds as 4 and total number of resonating structures as 3. So definitely this is your answer. 4/3 is the bond order present in carbonate ion, right? You can try on your own with respect to the nitrate ion, the bond order in nitrate ion. You can also find bond order in O3 molecule. So whichever resonating structures you may come across, you will be able to find the bond order. Please remember this formula. Yeah? Okay. Now moving on with the next set of questions here. The lattice energy of Kf, potassium fluoride, KCl, that is potassium chloride, potassium bromide, and Ki, potassium iodide, will follow any of these order, right? Now, understand here. First and foremost thing, these are all the ionic compounds, right? And they are definitely going to have a specific crystalline structure. And to break that crystal lattice, you may require some amount of energy, or when the lattice is formed, amount of energy will be released, right? So either way, you can consider the lattice energy. Okay, so the question is, of these ionic compounds, which particular ionic compound may have maximum lattice energy? And then obviously others will fall into the order. Okay, now remember this, that whenever we are dealing with any ionic compound, A plus B minus, okay, it is basically the electrostatic force of attraction which is holding these two ions together, right? And if you break these interactions, you will have to supply some energy, or when these interactions are formed, energy will be released. That is precisely, as I told you, is lattice energy, right? So the lattice energy for any of the ionic compound, lattice energy for any of the ionic compound, it depends on the internuclear distance between the combining ions, okay, the present between these two ions, okay, like here it will be K plus F minus, K plus Cl minus, and so on and so forth, right? So it depends on the internuclear distance. So one of the factor which determines is this. Right? And of course, another factor here is nothing but the charge on the ions. Now, if you notice here, because we are having a common cation here, that is K plus, and all the anions, they belong to the same group. So this charge on the ions may not affect the lattice energy here. Okay. So if you consider here, you are going to have K plus F minus, K plus Cl minus, K plus Br minus, and of course K plus I minus. So here you are going to have increase in the ionic size. The size of the cation is same. However, the F minus, Cl minus, Br minus, I minus, the size of the anion is going to increase. And because the size of the anion will increase, we can clearly understand here that the internuclear distance will also increase, right? Now, if the internuclear distance is increasing, right, so the attraction between the positive and negative charges will go on decreasing, yes or no? And definitely you can easily break the interaction, or when these ions are combining, amount of energy released will go on decreasing. So because of increase in internuclear distance of the combining ions, the amount of energy which is releasing when the crystal lattice is formed is going to be lesser, right? And that's the reason of all these, we can say that Kf has the maximum lattice energy, and we can say that Ki will have a minimum lattice energy, right? So definitely from all these options, your option A is the correct answer, right? So Kf greater than KCl, then Kbr, and then Ki. So such kind of questions you can expect, this is based on lattice energy. Similarly, you can expect some questions based on covalent characters or the ionic characters. So please keep all these factors in your mind. Okay, so this is based on the lattice energy. Now let us have a look at a similar question. It is based on the ionic characters, determination of the ionic characters. And you are having PbF2, PbCl2, PbBr2 and PbI2, right? Now again, if you notice here, Pb is a common cation here. So now, in this particular case, the ionic character or its counterpart, the covalent character, depends on the extent of the polarization. Greater the extent of the polarization, greater will be the covalent characters, right? So if you consider here, again Pb2 plus, so I am drawing a common cation here, so Pb2 plus, and of course if I consider F minus, Cl minus, you are going to have Br minus, I minus, right? Now logically you will be able to gauge the idea here that if it is I minus, then Pb2 plus ions will be able to extract the outermost electrons from I minus strongly, right? And hence the drifting of electrons will be maximum in case of I minus. And because electrons are drifted to the maximum extent, we can say that the extent of polarization is maximum in PbI2. Now because F minus is relatively smaller in size, its electrons will not be easily drifted towards Pb2 plus, and that's the reason the extent of polarization here is minimum. So I've told you that greater the polarization, greater will be the covalent characters, right? So we can say here that covalent characters are proportional to extent of polarization, right? So if they are proportional to the extent of polarization, then of course we can say that PbI2 will have a higher covalent characters. Now if I am saying that it is going to have a higher covalent characters, without any doubt its ionic characters is going to be least, right? So definitely PbF2 will have maximum ionic characters. Then of course PbCl2, then PbBr2, and finally PbI2, right? So here you will understand that your answer should be A, right? So please remember, whenever they are asking question based on ionic or covalent characters, please talk in the context of polarization. Now this is from a very famous rule we called as Fajan's rule, right? And what all factors will determine the ionic or covalent characters? Obviously here you are having extent of polarization, which will be determined by the size of the cation, the size of the anion, the charge on the cation, the charge on the anion. So there could be certain variations in these kind of questions. Yeah. Alright, so moving on to the next question here. Among the halides like NaF, NaCl, NaBr, Nai, NaF has the highest melting point. What is the reason for that? Now I'm sure you will be able to gauge the idea here that NaF, because it is having maximum ionic characters. Why? Because in NaF we can say that the extent of polarization is minimum. And because the extent of polarization is minimum, we can say that it is having the maximum ionic characters, right? All the more, Na and F, Na plus and F minus, their internuclear distance between the ions is also very small. So we can say that it has got very high lattice energy, right? So because of all these reasons, we can say that NaF has a maximum boiling point, right? And because of which, you will have NaF, NaCl, NaBr and Nai comparison here, right? So of all these options, if I want to choose, so here you are going to have minimum ionic characters, maximum ionic characters, highest oxidizing power, lowest valency. Now obviously option C and D, they don't make any sense here, right? So your option B is going to be the correct answer, because it is having maximum ionic character because of least polarization, right? So these are some of the questions which are based on covalent characters in ionic compounds, Fajan's rules. So please make sure that you are thorough with these concepts. Moving on with the next question here. Now this is the counterpart. This is another way. This is ionic characters in covalent compounds. Okay, and to determine ionic characters in covalent compounds, we have a specific parameter which is nothing but we call it as dipole moment. Okay, let's have a look at the question first of all. What they are saying is the observed dipole moment of HCl is 1.03 dBi. D is dBi here. If the bond length of HCl is 1.3 angstrom, then the percentage ionic character of HCl bond is. Now see, understand one thing, HCl is a covalent compound. However, it is a polar covalent compound. Why? Because of the electronegativity difference. So here we are dealing with, out of this basically the covalent nature, how much percentage is contributed by the ionic nature. So that is what we have to find here, percentage ionic character, right? And remember this formula, if you want to find the percentage ionic character here, so the formula is percentage ionic character is equal to observed value of mu. Mu is nothing but dipole moment here, okay? So observed value of mu to the theoretical value multiplied by obviously 100. This will give you the idea with respect to the percentage ionic character. Now in this question, they have already given you the observed dipole moment, which is nothing but 1.03 debye. If you find theoretical dipole moment, then we are done with this question. Okay, so before actually I discussed how to find the theoretical dipole moment, let me give you certain relations here. This is extremely important as far as the units are concerned. Okay, so first and foremost thing, mu is equal to Q times R. Q is nothing but the magnitude of the charge and R is the internuclear distance, right? Basically bond length we can say. Now generally we express this mu in the units of debye. Okay, and if I want to correlate this debye unit with different other units, then I'm going to give you this relation here that 1 debye is equal to 10 to the power minus 18 ESU centimeter. Now what is ESU here? Electrostatic unit, ESU centimeter, right? So this is one of the way, this is one relation between debye and ESU centimeters, and in terms of SI unit, that is coulombs and meters, here you are going to have the relation as 10 to the power minus 30 coulomb meters. Okay, this is another relation. Also, we already know the unit charge in terms of coulombs, right? So it is nothing but 1.6 times 10 to the power minus 19 coulombs. This we already know. In terms of ESU, 1 unit charge is nothing but 4.8 into 10 to the power minus 10 ESU, electrostatic unit. So depending on whatever unit has been given to you, you have to use these values and then get the answer for percentage ionic character. Now in this case, they have given you debye unit, right? And the bond length here has been given to you in terms of what angstrom unit, right? So this angstrom unit, you can convert that into the centimeters, right? And of course, you can also use this ESU. So we are going to find this in terms of what? CGS units here, okay? So here I can say that distance between two nuclei is 1.3 angstrom, which is nothing but 1.3 into 10 to the power minus 8 centimeters, right? Now, the charge we already know. We are going to consider here the charge as 4.8 times 10 to the power minus 10 ESU. Yeah? So the mu theoretical is going to be equal to Q times R, which is 4.8 times 10 to the power minus 10 into 1.3 into 10 to the power minus 8, right? So this will be approximately around 6.12 into 10 to the power minus 18. Now, this particular answer which you have got, 6.12 into 10 to the power minus 18, is in terms of ESU centimeters, right? And we know that 10 to the power minus 18 ESU centimeter is basically 1 debye. So I can say here that mu theoretical is nothing but 6.12 debye. Simple, straightforward, right? Now, here we have got the theoretical value, observed value is already given to us. So if I just now want to find the percentage ionic characters, can I say it is going to be 1.03 over 6.12 times 100. And this answer is nearly equal to 17%. Right? Okay, so definitely your answer is option C here. So when it comes to HCl, you will realize that in that case you are having H single bond Cl. So H is having a partial positive charge, Cl is having a partial negative charge. So because of these charges, there will be certain extent of ionic characters in HCl molecule, and that particular extent is just 17%. Yeah. So I hope you got the clear understanding. Please remember this particular formula to find the percentage ionic characters, and of course these values. Okay, these are the interrelations between debye and different other units and the unit charge values, right? Please make sure you know these by heart. Let us take a similar question here. The dipole moment of HBr is 1.6 times 10 to the power minus 30 coulombs centimeter unit, very important. And the interatomic spacing is 1 angstrom. Now the moment I say interatomic spacing is basically bond length. Again they are asking you to find the percentage ionic character, okay. So again we need to find first of all the theoretical value of mu, right. So here I can say that mu is equal to Q times R. This mu is basically the theoretical value. So Q value here, see, in the given or the observed dipole moment is given in terms of what coulombs, right? So the charge here I am going to write in terms of coulombs rather than writing in terms of ESU unit. So here it is going to be 1.6 times 10 to the power minus 19, right? And the internuclear distance has been given to us as 1 angstrom. And if you see the unit of length here is in terms of centimeters. So I will convert this angstrom into centimeters, which is basically here 10 to the power minus 8, right? So here basically you are going to get this answer as 1.6 into 10 to the power minus 27, right? Now this is in terms of coulombs centimeters, right? And if you want to find the percentage ionic characters now, okay, you have been given the value that is observed over theoretical. So here you are going to have 1.6 times 10 to the power minus 30 divided by 1.6 into 10 to the power minus 27 and of course into 100, right? So you'll realize that your answer comes out to be 10% here. So your option A is going to be the correct answer. So please remember these kind of questions and these kind of formulae, right? If they're asking you any question which is based on the percentage ionic character. So now moving on with the next part. Now this is the final part of this chapter, which is nothing but certain questions based on molecular orbital theory. Now on the basis of molecular orbital theory, what all kind of questions they can ask you? They can ask you the bond order, the magnetic behavior or the stability, right? And for that you should be having certain idea as to how to draw these molecular orbital diagrams, and that too quickly, okay. So if you look at this particular question, in which of the following ionization processes the bond order has increased? The bond order has increased and the magnetic behavior has changed. Now when I say magnetic behavior has changed, it may be from paramagnetic to diamagnetic or from diamagnetic to paramagnetic, it depends, okay. Now let us have a quick look here with respect to very first change here, N2 changing to N2 plus. Now we know that N2 molecule, the total number of electrons here are 14, right? 14 electrons. So definitely in such species the number of electrons, if they are less than or equal to 14, right, then the arrangement of the molecular orbital is going to be 2 1 2 1, right? So I'll just draw the molecular orbital diagram for N2 here. So 2 of the molecular orbital here, 1, again 2 and 1. Okay, so these two are obviously bonding and these two are anti-bonding molecular orbitals. And here nitrogen, one nitrogen here and obviously another nitrogen here, each having 3 unpaired electrons like this. So when you distribute these electrons into these bonding and anti-bonding molecular orbitals, so it's 1, 2, 3, 4, 5 and 6. That's it. So if I just consider N2 molecule, then its bond order is going to be equal to 6 minus 0 divided by 2, so definitely it is 3. And you can see that all the electrons in the molecular orbitals, they all are paired, and that's the reason it is diamagnetic, right? So I hope you get the clear understanding here. Now if you notice here, for N2 plus, you have to remove one electron. So let's say I am removing that electron from here, that's it, finish. So if I remove one electron from here, then its bond order will be equal to 5 minus 0 over 2, that is basically 2.5. So bond order has changed and in fact it has decreased. The moment you see here decrease, so definitely this cannot be your answer. Okay, all the more because there is one unpaired electron present, we can say it is paramagnetic. So that is true, right? It is very much correct. However, because the bond order has decreased here, we cannot say that this could be your answer, right? Now similarly, we can do it for C2 changing into C2 plus, NO changing to NO plus. Okay, now here if I'm considering this C2 changing to C2 plus and NO changing to NO plus, let's have a look at these molecular orbital diagrams. Okay, so we have C2 molecule, right? So again carbon has atomic number of 6, so its electronic configuration is 1s2, 2s2, 2p2. So let's quickly draw only the diagram with respect to p orbitals, right? So here you are going to have, here also you are going to have this, right? So 2p2 here, 2p2 here. Now again the number of electrons are less than 14, so the arrangement is going to be 2, 1, 2, 1. Okay, so if I put the electrons here, 1, 2, 3, 4, that's it, right? So it is diamagnetic for sure, and the bond order is going to be 4 minus 0 over 2. So the bond order is nothing but 2 here. So it is diamagnetic and having a bond order of 2. Now if I consider CO plus or C2 plus, you remove one electron from here. The moment you remove one electron, the bond order now will become what? 1.5. So again here bond order has decreased, isn't it? Bond order has decreased here. Now again if I consider NO molecule, now NO molecule is a typical example wherein the two nuclei are different, right? So we say it is heteronuclear diatomic molecule. So in such a case, you have to go with respect to drawing the molecular orbital diagram the way you have been doing for homonuclear diatomic molecules. The only thing you have to be a bit careful about is the placement of these orbitals. Now nitrogen and oxygen, because oxygen is relatively more electronegative, its orbitals I am going to draw little downwards, p orbitals, and for nitrogen I am going to draw it little upwards. Okay, and we know that there are 3 electrons in nitrogen in p orbitals, and of course for oxygen 1, 2, 3 and 4. Now if we count the total number of electrons, nitrogen has 7, right, and obviously oxygen has 8, so total number of electrons here are 15. So the number of electrons, because here there are 15, the arrangement of the molecular orbital is going to be 1, 2, 2, 1, right? So let's quickly draw this. One of the molecular orbital here, bonding molecular orbital, 2 here, again you are going to have 2 and 1. That's how the bonding molecular orbitals will be. And we distribute the electrons here. So 1, 2, 3, 4, 5, 6. 6 electrons already. Okay. In total we have to distribute 3 plus 4, 7. So you have one more electron here. Okay. So now in this case, if you see the bond order is nothing but 6 minus 1 over 2. So basically it is 2.5, right? And because it is having one unpaired electron, we can say it is paramagnetic in behavior, paramagnetic in nature. Okay. Now if we consider NO plus, what is happening here? Remove this electron. If you remove this electron, in that case the bond order will become 6 minus 0 over 2. So definitely bond order is 3. Is the bond order increased? Answer is definitely yes. All the more, is the magnetic behavior changed? Definitely yes. Why? Because now all the electrons have become paired. So it is definitely going to be what? Diamagnetic. Right? So this is basically for NO and this is for NO plus, right? So if you realize that of all these options, when you do the working, option C is your correct answer. Yeah. So as I told you, based on molecular orbital theory, they can ask you about bond order, they can ask you about the magnetic behavior and also the stability order. Okay. Let us have a quick look at one more question and then we'll conclude for today's session. So here you are having CF and they're asking you the increasing bond length. Now, in order to find the order for increasing bond length, you should be having an idea about the bond order as well. Okay. So if I consider CF CF plus and CF minus. Again, we know that carbon atomic number is 6, so it is 1s2, 2s2, 2p2. Fluorine atomic number is 9, so it is 1s2, 2s2, 2p5, right? So let us quickly draw the molecular orbital diagrams. So for p orbitals for carbon, it's going to be here, and fluorine, I'm going little downwards here. So 1, 2, 1, 2, 3, 4 and 5. Okay. Now number of electrons are definitely greater than 14. So the arrangement is going to be 1, 2, 2, 1, right? So I put this here as 1, 2, 2 and of course 1. Yeah. And now let's quickly distribute these electrons. So here you are going to have 1, 2, 3, 4, 5, 6. So in all, we have as of now distributed 6 electrons. Now total you are having 7 electrons, so 1 electron will be here, right? Now this is the molecular orbital diagram for CF molecule. This is C, this is F. This is for CF. So here I can say that for CF, the bond order is equal to, you can say 6 minus 1 by 2. So basically, bond order is nothing but 2.5. Okay. Now, if I consider CF plus, right? So if I consider CF plus, just remove this part. So if I are removing this part, the bond order will become 6 minus 0 by 2, that is nothing but 3. Yeah. Again, coming back to CF. And CF minus, you are introducing one more electron, so that obviously is going to go to anti-bonding, right? So in this case, the bond order is going to be 6 minus 2 divided by 2. So basically bond order is going to be 2. Now, the thing is, if they're asking you increasing CF bond length, right? So if the bond order is larger or having a higher value, that means the atoms are closer to each other, right? They are closer to each other. So if I'm saying that CF plus has the highest bond order here, that means its bond length will be least. Okay, so we can say here the order is going to be CF plus having least bond length followed by CF followed by CF minus. In other words, we can say that CF minus has maximum bond length. Yes, so these kind of questions you can expect in your entrance level examinations. So I hope you got the clear understanding with respect to overall idea about the chapter of chemical bonding. That was all from my side. Thank you very much.